Almost every local LLM benchmark measures the wrong thing. We track a single call, first token in, answer out, and the hardware looks fast. But an agent doesn't make one call and stop. It runs a continuous loop. It thinks, calls a tool, reads the result, and thinks again, repeating that cycle until the task is complete. On local hardware, the slow prefill phase you paid for on turn 1 gets paid again on every single subsequent turn, and it gets paid against a context window that constantly expands. The box that aced your one-shot test will crawl across a 10-step task. One call looks fast, but 10 calls compound. The loop, not the call, is the unit that defines your actual latency. I'm the bearded AI guy, and this is day 6 of the Poor Man's Spark series, where we deploy real agents on local large language models. The data we're looking at today is new hardware research, built on top of a foundational theory laid out in the Human Architect's book, AI Agents in Action. The first 5 days of this series measured single calls in isolation. Today, we measure orchestration. This is the moment where hardware weaknesses stop averaging out and start stacking. If you've ever wired up a local agent that felt snappy in testing but sluggish in production, this explains why. Mapping these specific architectural bottlenecks is the only reliable way to successfully deploy agents on your own iron in 2026. To understand why these loops drag, you have to look before it can say anything. Second is generation, actually emitting the next move. Generation speed is a fixed wall. On a unified memory budget box, your raw memory bandwidth dictates a hard ceiling, usually topping out somewhere around 256 to 273 gigabytes per second. The third bill is the tool's execution time. This runs entirely on the CPU side and operates independently of the model. Because generation bandwidth is a hard cap, prefill becomes the dominant variable. With every turn, the context history gets longer, and that first column grows taller. You pay a heavier tax on step 5 than you did on step 1. End-to-end loop latency is almost entirely controlled by the compounding bloat of that prefill phase. Think of this mechanism like filling a bathtub, where the faucet gets slower every time you add a scoop of water. The first scoop is quick. By the 10th, you're waiting, because there's more volume to push through the pipe each time. This chart measures that slowdown on physical hardware. We're looking at an RTX 4090 running Llama 3.1 8B through LangGraph and Ollama. Average turn latency lands between 1.8 to 3.5 seconds. Over a 2 to 4 iteration query, you're looking at roughly 4 to 14 seconds end-to-end. And that is the floor, a small model on the fastest single consumer GPU. Swap in a 70 billion parameter model on a low bandwidth machine, and that curve inflates. The prefill term grows, and you pay for it on every single step. This compounding penalty breaks local orchestration unless you aggressively manage the context footprint. When developers see slow loops, the common instinct is to fan out, spawn 5 parallel subagents to research 5 sources at once, and expect a 5 times wall clock speedup. But look at the serving stack. On the left, a Llama uses a standard FIFO queue. Those parallel requests effectively serialize. They line up and resolve one at a time. On the right, VLLM uses continuous batching, allowing the requests to overlap in the processor core. Even with batching, you're limited by how much memory the box has. On a single machine, every agent draws from the same pool of VRAM to store its conversation history. If your total context window is W, and each agent needs M tokens for its messages, you hit a hard ceiling where N equals W divided by M. Past that point, the hardware can't fit another agent's history into memory. Adding more agents doesn't just stop helping, it causes the entire parallel execution to fail as you hit the context limit. Deploying multi-agent swarms locally is entirely dependent on continuous batching support, and even then, your scale is strictly bounded by the hardware's context limit. When a long loop finally pushes against that context limit, the standard practice is to ask the LLM to summarize the history and start fresh. But summarization is itself an inference call. The model has to read everything you've done just to write a recap. You are paying for a massive, worst-case prefill penalty at the exact moment your context is the largest. This diagram breaks down the optimized alternative, observation masking. Instead of passing the entire history back through the model, you prune the data on the CPU side. Old tool outputs fade out into placeholders, keeping the reasoning traces intact without triggering an extra model call. The dead weight in these loops is almost always the raw tool outputs. Data shows that just 5 tool results can eat 81% of your total context. Masking simply unloads them. The design rule for local hardware is clear. Summarize freely on cloud APIs, but locally use masking to avoid paying for an extra slow prefill. All of these constraints point us to a heuristic for when to deploy locally. If a human is waiting synchronously for an answer, slow loops hurt. If nobody is waiting, they don't. The left column lists the strong local wins: overnight batch processing where latency is invisible, air-gapped workflows where local hardware is a compliance mandate, and high-volume repetitive tasks where an owned box amortizes the cost. The right column details the weak fits: latency-sensitive interactive agents with long contexts, and high-concurrency bursty workloads that slam into the memory ceiling. Local versus cloud is not an ideological choice. It is a pure engineering trade-off, dictated entirely by your acceptable loop latency. Compounding prefill, the batching trap, and context overflow all collapse into a single metric: end-to-end loop latency. Once you measure latency, the architecture answers itself. A single process splits into 2 distinct branches. Execute the many routine tool calling steps locally where they are free, then route rare hard synthesis steps to a cloud API for frontier quality. Because modern frameworks only interface with a base URL, you can implement this routing in your code without changing how the agent actually functions. The question isn't whether local hardware is good enough. It's a calculation of the loop itself. Measure that latency, then route by it. Want more technical breakdowns of local hardware and AI architecture? Subscribe to Bearded AI Guy. Drop a comment with your exact orchestration stack, and let me know if you are successfully achieving continuous batching parallelism. The hardware research in this episode builds on the foundational theory laid out in the Human Architect's book, AI Agents in Action. The book gives you the core mechanics. Our testing shows you where the metal bends. The optimization to leave you with: mask your stale tool outputs. Stop paying for a prefill you don't need.